Okay, welcome everyone to the new semester of the Every Person Dynamical System and Number Theory, Dynamical Systems and Number Theory seminar. So we'll try to meet most of Thursdays this semester, this time period, and it's 1 hour and 15 minutes, but it could be a bit shorter, or it could have a break and then continue. We're quite flexible. So I hope you'll come often, and let me turn this over to Felipe to introduce the speaker.
Okay, welcome everybody. Today's speaker is Simon Baker from the University of Loughborough. He'll be speaking on overlapping iterated function systems from the perspective of metric number theory. Go ahead, Simon.
Thank you very much, Felipe, and thank you very much for the opportunity to speak. So, so to begin, I'm just going to introduce a few kind of basic concepts from fractal geometry. Now, I'm not entirely sure, of everyone's background here, so let me just say, if at some point in the talk you want me to pull things back and recall some notion from fractal geometry which perhaps you're not readily familiar with, please feel free. Okay, so so yeah, now to begin properly, so I'm going to be interested in collections of maps, and these maps are going to be contractions. And here's the definition of a contraction. So a map is a contraction if it uniformly distorts the distance between points. And we call a finite set of contractions an iterated function system, or an IFS. And once you have an IFS, you can associate a special set to it. There exists this unique non-empty compact set X, which satisfies this relation here, namely that X is equal to the union of its images under the elements of the iterated under elements of the iterated function system. And we call this X the invariant set of the iterated function system. And typically this set X will look like a fractal set. Okay, so here's an example, probably an example we all know. If I take these two maps, I take the map X goes to X over 3, and the second map X goes to X plus 2 over 3, then this IFS has the middle third Cantor set as its invariant set. So those real numbers whose base 3 expansion only contains 0 and 2. And I just want to emphasize here that X has this property that if you look at the images under the two maps in the iterated function system, well, then these two images, their intersection is disjoint. The intersection is empty, rather, they are disjoint. And in a sense, these are kind of simple iterated function systems. I'm going to be interested in ones which have significant overlap, for which this intersection will certainly be non-empty. And we'll see an example in just a moment of such a system which I'm interested in. Oh, I thought there was another slide, but yeah, here's that example straight away. So now what I do, instead of contracted by a factor of 1/3, I take some parameter lambda between 1/2 and 1, and I associate two maps. I have the first, which just takes x to lambda x minus 1, and the second, which takes x to lambda x plus 1. Then it's fairly simple to show that in this case, the invariant set is no longer kind of a proper fractal set, but it's in fact this interval here. But importantly, this interval, when you consider that it's two images, they're going to have non-empty intersection. In fact, this intersection has non-empty interior. And these are somehow the more interesting iterated function systems, because somehow these pieces overlap in this significant way. Now, to study these fractal sets, it's kind of typical to introduce measures supported upon them, and to study properties of these measures. And the most commonly studied family of measures are defined as described on this slide. So you need two ingredients. You need your iterated function system and a probability vector P. Then there exists this unique Borel probability measure mu P, which satisfies this relation here, namely that mu P is equal to this convex combination of its push forwards, where the push forwards are under elements of the iterated function systems, and the weightings in this convex combination come from the probability vector. And these measures are very well studied objects, and somehow they often provide an easier route to determining metric information about your fractal set, your invariant set. So if you don't like this, the notion of this measure, here's a particular example which it's good to have in mind. So if we take this example I had a few slides ago, the iterated function system where I have lambda between 0.5 and 1 and these two maps, then if you take your probability vector p to be a 0.5/0.5, then the measure mu p is the law of this random variable here, where you think about this power series where you take a plus or minus lambda to the I, where plus is chosen with probability 0.5 and minus is chosen with probability 0.5. And this family of measures are known as Bernoulli convolutions. And for this family, often the properties of these measures are often kind of wrapped up in the algebraic and number theoretic properties of the lambda. These are very well studied, a very interesting family of measures. But now I'm going to start kind of, so far I haven't said anything about kind of metric number theory or Diophantine approximation. Why does this start to creep in? So it's very easy to show that if you were to fix a Z in your invariant set, and you were to look at all of its images under n-fold concatenations, the elements of the iterated function system, look at Dirac masses weighted at these images, Dirac masses located at these images, weighted by certain probabilities. So this is just this expression I've written here, a collection of Dirac masses centered at these points with some weight. Then the weak star limit of this measure, in fact, is equal to this measure mu p. Okay, so just to emphasize a bit of notation here, if I have a finite word of length n, then I'm going to denote p subscript a by the corresponding by the product of the probabilities corresponding to the entries in this word, and I'm going to denote by this this map here, subscript a, to be the composition of the maps corresponding to the entries in this word. Okay, so these measures, which somehow are very useful in studying these fractal sets, these invariant sets, these are somehow all of the properties we're interested in, whether the dimension, whether they're absolutely continuous, all these properties can be seen somehow as properties of the distribution of these numbers, the distribution of these images of your fixed point Z under concatenations of elements, the iterated, under repeated compositions of maps coming from your iterated function system. Okay. So now we start to see why maybe we could think about this in terms of Diophantine approximation. Somehow we're looking at the distribution of a collection of numbers lying in Euclidean space. To somehow make this a bit more formal, if I take we can kind of draw an analogy between these images of our point Z and the rational numbers or rational vectors lying in higher dimensional Euclidean space. If we look at all of the union of all of these images, well, they are dense in the invariant set. And as n increases, if you were to look at all of the images corresponding towards a level n, they become progressively more dense. So somehow we can see that, if you think about the rational numbers, they're obviously dense in the real numbers, and they have a tiering described by their denominator. Here, somehow we have this set, which is again dense, and its tiering comes from the length of the word corresponding to the image. So now I've kind of drawn this analogy, we can start to say, okay, can we study these iterated function systems using ideas from Diophantine approximation? And in particular, there are kind of three questions which I think are very natural to study. So particularly, we could ask ourselves, do we observe kind of classical behavior from Diophantine approximation in this new fractal setting? Is this interpretation essentially good for anything? It's kind of cute to say, okay, I could draw this analogy between Diophantine approximation, but in fact, does it allow us to say anything meaningful about iterated function systems? In particular, I'm interested in whether you can get a kind of a more interesting classification of iterated function systems when you view them from the perspective of Diophantine approximation and metric number theory. And last of all, you could ask yourself, okay, with this interpretation, do you get any kind of new interesting insights into existing results, things we've known for a long time? And what I want to convince you in this talk is that the answer to each of these questions is yes. Okay, so let me start to be a bit more formal and kind of more closely detail this this analogy between Diophantine approximation and somehow approximations provided by these images of your point in your fractal set. So, so just to recall, we have this very well-known result of Khintchine, which somehow describes the Lebesgue measure of a very general family of lim subsets coming from Diophantine approximation. I have my function psi from the natural numbers to the positive reals, and I can define a lim subset as follows. So I'm interested just in those x, which can be approximated by a rational p over q with error psi of the denominator, so psi of q. And then we have this kind of old result, which tells us that the Lebesgue measure is, well, under certain monotonicity assumptions, the Lebesgue measure is determined by the divergence or convergence of these summations here, which arise very naturally. So somehow I'm interested now in saying, okay, in this first question I answered, do we observe analogs of classical results from Diophantine approximation in this fractal setting? Well, the first result I'm going to be interested in is whether there is an analog of Khintchine's theorem for these sets. So, so let me kind of define the lim subsets I'm going to be interested in this fractal setting. So I have my point Z, which I fixed in my invariant set, and I'm going to be interested in how its images kind of distribute within my invariant set. And kind of how do I define my lim subset? Well, I introduce this function psi, which instead of being a function from the natural numbers to the positive reals, is now going to be a function from words of finite length to the positive reals. So now when I look at an approximation, I'm interested in whether x can be approximated by an image of z under the map corresponding to the word a, where the error is the image, is the whatever psi of a is. Okay, it's often kind of just to get some good intuition, you might want to just think that psi is a function which just depends simply upon the length of the word a. Okay, and there's been lots of papers that study this this topic. So in particular, there's some work by Alan Barani, there's some more work by myself, some other work by myself and Sasha Troscheit. There's some older work by Lebesgue, Salp, and Villani, and there's also some work by Pearson and Reeve. And then, well, I've mentioned these authors because they kind of share a similar perspective to myself, where it's more about the distribution of these numbers within an arbitrary fractal set instead of perhaps the perspective which comes from this question of Mahler on intrinsic Diophantine approximation, where somehow you're looking at special rational numbers between your fractal set and trying to understand how well these can approximate your elements of your fractal set.
Okay. Simon, just a quick question. So this set W phi, it is, I mean, it's the subset of RD, but in fact, it's the meaningful part is in the fractal. Right? So,
yes, as long as your psi converges to 0, it will be in the fractal set. Yeah.
Mm-hmm. Okay, but can you interpret it in the way so if you have this fractal, at least if it's say satisfies open set condition, then you can kind of invert these contractions and consider the expanding map.
Yes, you can. You can.
And this set has something to do with the dynamics of this expansion.
Yes, you're absolutely right. But I'm always going to be interested in the case where the open set condition doesn't hold.
Oh, right.
Which is somehow a lot more meaningful.
Yeah,
you jumped the gun by one paragraph.
Okay.
So so I'm always going to be interested in the case where the iterated function system is going to be such that our invariant set has positive Lebesgue measure, and we're going to have kind of significant overlaps. Mm-hmm. And the reason is we get a lot more interesting behavior this way. So let me go back to these examples I mentioned at the start, because this somehow...
Oh, I have a question. So, yeah, so sorry, I didn't follow why you need open set condition, because if you just think about the shift map, like if you just shift it to the, if you just think about the shift, like a shift to the left dynamics, I kind of don't see where you would need the open set condition when you thinking about it.
The question to me or to Simon?
Oh, like, I guess to both.
So Simon doesn't want open set condition at all. He wants overlaps.
Yeah.
And I was asking a question, so I don't want anything. So I think we should forget about open set condition for now.
Oh yeah, yeah. Okay, yeah.
I think so. So one could reinterpret things symbolically, but the problem is when you kind of pull things up to the symbolic space, the pre-image of a ball is going to be extremely complicated. You know, when in a properly overlapping system, if you have something like the open set condition or something similar, when you pull things up to this, into the symbolic setting, things are reasonably tame. Whereas what I'm looking at, the symbolic description is just going to, well, it's not going to give you any kind of meaningful new perspective. Okay. So I said I was interested in when things are properly overlapping, and I wanted to talk about these examples I mentioned at the start. So we have the middle third Cantor set here. And here it's not too difficult to show that if you kind of look at the natural measure on the middle third Cantor set, which is this, the log 2 divided by log 3 dimensional Hausdorff measure restricted to x, then, well, in fact, almost every point can be approximated with an error 1/3 to the n. When you take, say, z equal to 0. In fact, every point can be approximated with an error 1/3 to the n. And the point here is that this 1/3 is just simply coming from the contraction ratios. Okay, so somehow the quality of approximation you can see in a well-separated system just comes from the contraction ratios. Okay, but here the situation is very different. So for these overlapping systems, so here a typical point can be well, for certain lambda, you can expect that a point will be approximated with error 1/2 to the n. And 1/2 to the n is certainly not equal to lambda to the n. So when you're overlapping, the approximation is no longer determined by your contraction ratio. It's more to do with the number of points you have lying in your fractal set. Okay, so this is kind of a subtle change, but it means things are a lot more complicated, but a lot more interesting. Okay, so where was I? Yes, so so I want to just kind of recall the second question I mentioned about obtaining kind of a meaningful classification of iterated function systems using these ideas. So here's a very simple observation one can draw. So suppose I have two iterated function systems that belong to some parameterized family, like these Bernoulli convolutions, this example we saw a moment ago. And suppose I could find a psi and 2 points z1, z2, such that the corresponding limsup set for one of these iterated function systems had full measure, but for the other it had 0 measure. Then this would somehow tell me that the images of z1 under the iterated function system phi1 are more nicely distributed than the images of z2 under phi2. So this allows me to, this Diophantine framework gives me somehow a language by which I can compare the overlapping behaviors of iterated function systems. I could say somehow that the first iterated function system behaves better than the second from the perspective of the function psi. Okay, and in fact, we'll see a concrete example later where this is made precise, and we can give an explicit family where we can make these sorts of statements. But I just wanted to mention this here. Okay, so remember I mentioned we were shooting for an analog of Khintchine's theorem. So the first thing to say is that it's very easy to show if you're iterated function systems in d-dimensional space, that if this quantity here converges, then you're going to have 0 Lebesgue measure. So the question now becomes, does divergence imply full measure? And it's certainly not true in full generality, so we have to restrict to a particular nice class of psi. So I'm going to be interested in psi of this form. So I have this fraction here, I have this function h, which is from the natural numbers to the positive reals, and then I divide by the number of words of length n. So somehow the denominator, which is the number of words of length n, this is somehow the best, oh sorry, and this is all raised to the power of 1/d. Somehow this 1 divided by the number of words of length n, this is somehow the best exponential quality of approximation you could hope to see. And the h is going to give you some sub-exponential improvement over this. You could really think that h of n is going to be perhaps something polynomial converging to 0. But this is somehow, these are the psi we're going to be interested in from here on. And a very useful thing is that if I look at this quantity here, which I saw convergence implied 0 measure, then this simplifies just to the summation of something just over h to the n. So somehow now I'm hoping that the divergence or convergence of this summation of h will determine the measure of these lim subsets. In particular, I hope that divergence will give me full measure. Now, this is not true for every h, and I do need to introduce some restrictions. So so I have these two properties here. I'm going to speak of a function h being good if it satisfies these two properties. So the first is somehow a more substantial divergence condition. So I'm interested in full measure statements. I want a divergence condition. So this is something slightly stronger. This is saying that I can find an epsilon such that for any infinite set B, which has upper density greater than 1 minus epsilon, if I restrict my summation to this set, I'm still going to have divergence. So it's not just divergence, it's saying you could, for any sufficiently large set, if you restrict your summation to it, you'll still have divergence. Okay, so it's something slightly stronger. And then we have this kind of weak assumption, which just says when you consider successive terms, h of n plus 1 is never going to be significantly less than hn. Okay. Now, if you don't like these two conditions, you can just think of the function hn equals 1 over n. It's fairly easy to show that this function is a good function. Okay. So yeah, if you don't like these, just think of h of n being 1 over n whenever I say a function is good. Okay. Okay, and a further comment just to make is that the study of these limsup sets, well, they're extremely, these limsup sets are extremely delicate when it comes to an exact overlap. So what do I mean by an exact overlap? Well, my iterated function system contains one if I can find two words, A and B, which are distinct, but such that if I look at the corresponding maps, corresponding to the word A and the word B, these coincide. Okay, so somehow, somewhere within my system, there's some degeneracy, which means these two maps coincide. Then if there exists two such maps, if there exists an exact overlap, then for any bounded h, this lim subset is going to have 0 Lebesgue measure. And this is somehow what makes describing the behavior of these sets very difficult, because often the parameterized family of iterated function systems we're looking in, there will be a dense set which has an exact overlap. So somehow you're having to maneuver amongst these bad parameters, which you know you're going to have 0 Lebesgue measure, and you're still going to hope that you're going to have full measure statements. So here is a first positive result. So this is for the Bernoulli convolution. So basically, this theorem states that for almost every lambda in some interval, for this iterated function system, we're seeing Khintchine type behavior. So it's that for almost every lambda in this interval, for any good h, Lebesgue almost every x is going to be contained in this lim subset here. Okay. And I've written this in a slightly different form, just well, perhaps simplified a little things, but here the relevant IFS was this one given here, lambda x minus 1, lambda x plus 1, and I take z equal to 0. So somehow this is like approximations by kind of truncated power series in lambda with coefficients minus 1 and 1. Okay, but here we're seeing Khintchine type behavior already. So this is a particular, so yes, so we can say in this overlapping setting, we're already seeing some Khintchine type behavior. And it's interesting, again, to know that for this family, between a half and this parameter 0.668, which I just mentioned is there for technical reasons, I expect this theorem will be true from a half all the way up to 1, but I can't prove it. Within this parameter space, there's a dense set of bad parameters, which we know this lim subset will have 0 Lebesgue measure. So this makes the analysis kind of a bit more interesting. So now I want to talk about another family of iterated function systems, which again, we're going to see an analog of Khintchine's theorem. So what do? Well, here I have a finite set of matrices, each with norm at most 1. And then what I do is I randomly choose the translations from Euclidean space. So I have a vector t, it's bold t, which lies in d times the number of elements in my iterated function system dimensional Euclidean space. And then to each one of these blocks of length d, I'm going to associate a translation vector, and that's going to tell me the translation I apply once I've applied my matrix ta to a point x. Okay, so you see this vector determines this iterated function system here. Okay, so this is again is giving me a parameterized family where the parameter is this bold vector t. So I have this invariant set which is going to depend upon t. So I have x subscript t. And then I also have this map, which is quite useful, which goes from the symbolic space to my invariant set, which is just this natural projection map, okay, which just takes a sequence and associates to it a unique point in the invariant set. Okay. So yes, so for this family, we do observe an analog of Khintchine's theorem. I'm going to state it now, but I just need to, there's a lot in this statement, so I just want to introduce it slowly. So first of all, I need to assume that all of these matrices have a norm at most 1/2. And I also have this assumption that the Lyapunov dimension exceeds 1. Now, I'm not going to state what the Lyapunov dimension means. Essentially, you can think of it as meaning that you have enough matrices to expect that the invariant set would have positive Lebesgue measure. You could just think of it as having lots of matrices, lots of maps. Okay. So under these assumptions, the conclusion basically is, again, we're going to see Khintchine type behavior. We're going to have that if you fix a sequence Bj, for Lebesgue, almost every translation, if you consider the limsup sets, which is going to be located at the images of the projection of Bj, look at approximations provided by these images with this error determined by some function h, then this set is going to have positive Lebesgue measure. Okay. And it's natural now to ask, okay, well, what can you upgrade positive Lebesgue measure to almost every element in the invariant set? You can do this, but you need a bit more information. And that's the content of this slide here. So essentially, you can go from positive Lebesgue measure to to almost every point in your invariant set if you were to assume that each of your maps were a similarity. So this would be your affine, your matrices would just be some orthogonal matrix multiplied by some constant lambda. Or maybe if you're in d equals 2 and all your maps would coincide, or your TI is simultaneously diagonalizable, blah, blah, blah. If you have any of these assumptions, then you can step from positive Lebesgue measure to almost every point in the xt is contained in this limsup set. So yes, so these results, I mean, the second was a bit more messy to state, but hopefully they should convince you that for these overlapping systems, we're seeing analogs of Khintchine's theorem when we consider approximations provided by these images of Z. And just a comment is that we can consider slightly more exotic functions psi, which aren't just going to depend upon the length of the word A. So in fact, if I have a nice measure mu on symbolic space, we can define a family of psi by just looking at psi of A being the measure of the cylinder corresponding to the word A multiplied by the function h. So somehow the exponential decay is determined by the measure of the cylinder, and h is some sub-exponential improvement upon this rate. And for certain nice measures, we have kind of analogous results which are slightly more complicated to state. Notice that if I was to take my measure to be the uniform measure, then every cylinder of length n is going to have mass, well, 1 divided by the number of words to the power of n. So that would just, so taking this measure m to be the uniform measure, I would be in the framework we've just seen. Okay, and a final comment, a final theorem I wanted to mention, which is quite easy to prove, is just if you ask yourself, how does this, observing analogs of Khintchine's theorem compare to kind of more traditional notions for understanding properties of measures? So in particular, how does it compare to, say, absolute continuity? And what this theorem tells you is that if you see an extremely strong version of Khintchine's theorem, namely that if for any h which you have divergence, the lim subset is going to have positive Lebesgue measure, then in fact, this measure mu p is going to be absolutely continuous. So somehow this is observing this Khintchine's type phenomenon is really giving you some, if we wanted to kind of describe how these measures behave, somehow we could say a really strong, somehow having exhibiting really strong Khintchine behavior is somehow, stronger than absolute continuity and stronger than whatever you know about the dimension of the measure. It's a really special property. But it's interesting that you can relate these things. Okay, so
excuse me, just curious here. Are you assuming that h is non-increasing, or it's not necessary?
It's not necessary.
So you want it to be good instead. Okay, thank you.
Right. Right. So now I wanted to mention one specific family of iterated function systems, and this family is very useful because it allows us to see how these kind of limsup sets allow us to compare the overlapping behavior of iterated function systems. So here's a parameterized family. Given number t between 0 and 1, I associate these four maps. So yeah, I have x over 2, x plus 1 over 2, then x plus t over 2, and then last of all, x plus 1 plus t over 2. And it's very easy to show that this self-similar set, the invariant set in this case, is just this interval 0 to 1 plus t. So it's not particularly interesting in terms of a fractal set, but yes, but the way it overlaps and the way it depends upon t is very interesting. So just to establish a bit of notation here, for this family of iterated function systems, I'm going to note by WT H Z this lim subset. Okay, so H is again just going to be a function from the natural numbers to the positive reals. I divide by 4 to the n because I have 4 maps and I'm looking in one-dimensional Euclidean space. And yes, and I'm interested in approximations provided by the image of Z under the word A with this error H of n divided by 4 to the n. The dependence on T here comes in this in the maps. In the map, yeah, these maps depend upon T. It's not immediately, yeah, the way I've written it, you don't see the dependence, but these maps depend upon T. Okay, so what do we know? So if your T is rational, then your iterated function system contains an exact overlap. And in fact, you see nothing at all like Khintchine type behavior. I mean, we saw this before. If you were to take your H to be the constant function 1, then in fact, not only is it going to have Lebesgue measure 0, but the Hausdorff dimension of the corresponding lim subset is going to be strictly less than 1. This is very easy to show. But something slightly more interesting is that if T is irrational, then you're going to see some sort of Khintchine type behavior. You're going to be able to find a H which converges to 0, such that for any Z, Lebesgue almost every X is going to be contained in this lim subset. So this is quite an interesting dichotomy we're seeing. We're either seeing an exact overlap, somehow Khintchine type behavior is immediately ruled out, or you don't see an exact overlap, and you see some sort of Khintchine type behavior described by this function H. And for those of you who do a bit more, you know a fair bit of fractal geometry, this might seem natural because a lot of results in fractal geometry go along the lines of, well, a lot of conjectures basically on the lines of you will either see a behavior or you won't, and what determines it is the presence of an exact overlap. So this somehow fits into that framework. But the next two results show that in fact, well, the next two statements in fact show that something a bit more subtle is going on, that it's not just a dichotomy in terms of exact overlap and not an exact overlap. We can show that if T is badly approximable, then for any H for which you have divergence, you're going to have that for any Z, almost every X is contained in this lim subset. But if T is not badly approximable, then you're going to be able to find a H for which you have divergence, yet the lim subset is always going to have 0 Lebesgue measure. So somehow, yeah, we're seeing something slightly more subtle going on. We're seeing amongst T's which are not rational, so you don't have an exact overlap, we're seeing kind of different types of Khintchine behavior. And just one thing I wanted to emphasize here, I gave this talk a little while ago. And when I stated these two results, I remember some people in the audience started to mutter about this theorem of Kurzweil, which kind of bears a strong resemblance to this, which I imagine many of the participants are aware of. However, this theorem is not Kurzweil's theorem written in a different language. I expect that the underlying mechanisms by which you prove these statements are similar, but these are different statements. It was just something I wanted to emphasize. Was there a question? My sound went weird for a moment. No? Okay, I'll carry on. So remember these last two statements. We have these T for which we can see kind of differing degrees of Khintchine type behavior. Now, you can take this theorem from the previous slide and you can combine it with some kind of big breakthroughs in fractal geometry recently to show that you have a T and a T prime such that the iterated function systems phi T and phi T prime satisfy the following statements. So I have this first statement here where I've introduced some notation which I haven't defined, is to do with the dimension of these measures, these mu p's. And essentially this first statement is telling you that the dimension of these measures, which is some way of describing the size of these measures, these are always going to coincide. Okay, no matter if for both t and t prime, these measures are going to have the same dimension, so you can't distinguish them in terms of the dimension of the measures. Then when you look at the next point, when you look at the set of p's for which the measure mu p is absolutely continuous for the map for the iterated function system phi t, well, this is going to coincide with the set of p for which mu p is going to be absolutely continuous for the iterated function system phi t prime. So somehow in terms of dimension, absolute continuity, you can't tell them apart. But when we think of them in this new metric number theory, Diophantine approximation way, we can distinguish between them. We can find this H, which allows us to say this lim subset has zero measure and this lim subset has full measure. So somehow this, a quick summary of this slide is somehow saying these iterated function systems are indistinguishable when we just look at these measures mu p, these self-similar measures. But when we put on our Diophantine approximation metric number theory hats, we can distinguish between them. And that's somehow one of the values of this approach. Okay, so now I'm going to say a little bit about the proofs of these statements. So they all roughly follow a similar strategy. So the first step and the most crucial step is you fix your point Z, which is going to generate the points that you use to define your lim subset. And what you want to do is you want to show that there exists two constants, C1 and C2, and a large set B, for which you have the following. For any n in B, you're going to be able to find a large collection of the words of length n. So by large, I mean their cardinality is comparable just to the words of length n, such that if you look at the images of Z under any two words in this set, which are distinct, the distance between them is somehow going to be optimal. It's going to be larger than a constant, namely this constant C2, divided by the number of words of length n, all raised to the power of 1 over d. Somehow, by a pigeonhole argument, you can see that this scale of separation is somehow the optimal level of separation. When you look at all these points, you're going to have two for which the distance between them is going to be at most a constant times 1 divided by these number of words of length n to the power of 1 over d. What this statement is telling you is that you can find a large, well-separated set at level n, for which you're going to see kind of optimal separation. And the optimal is we can see this because of this by the pigeonhole principle. So somehow this first step is the most difficult step. This is the key step. And once you've established it, it's fairly easy to prove that the following lim subset is positive Lebesgue measure. So basically this is just, this is a subset of the actual lim subset we're interested in. And essentially all we do is we're just interested in those levels coming from B, for which I know I have this large, well-separated set. So this is, instead of unioning over all n here, I union over this all n larger than big N, for which n is contained in B. And instead of considering all images, I look at images coming from these words, which I know the images are well separated. Okay, and then just by some fairly simple quasi-independence on average estimates, you can show that this has positive Lebesgue measure. Yeah. Then when you want to go from positive Lebesgue measure to full Lebesgue measure, you have to do a bit of work. And this is when kind of these properties of H come in. Using the fact that H is good, it allows you to often step from positive Lebesgue measure to full Lebesgue measure. Okay. So as I say, the key step is 1, somehow being able to say that for infinitely many levels n, you're going to have this large, well-separated set. And to do that, we study this quantity here, which is some kind of pair correlation quantity. We look at all of those pairs of words of length n, which are different, for which the distance between them is less than or equal to some constant s divided by the number of words of length n to the power of 1 over d. And what I claim is that for certain nice parameterized families of iterated function systems, this quantity can be studied. This is using the transversality method due to Solomyak, and this originally appeared in this work of Benjamini and Solomyak. And then for this family, for which we are able to make these very precise statements, you can study this quantity just using the Diophantine properties of T. Okay, But the point is, this is somehow a very nice quantity, well, this is somehow a very amenable quantity to study using analytic methods. And if you can bound this, you can assert that there exists large, well-separated sets. Okay, so I just now want to give you a bit of an insight into this transversality technique and how it can be used to bound this quantity. So we're going to be talking about this iterated function system, this example of an iterated function system we saw at the start, where lambda is some parameter between 0.5 and 1. And we look at these two maps, lambda x minus 1 and lambda x plus 1. And there is this lemma of Solomiac, which tells you that if you have, well, if you restrict to some interval between 0.5 and 0.668, then if you look at any power series, well, any function g of x of the form 1 plus a power series where the coefficients are -1, 0, and 1, then if you look at the Lebesgue measure of those points for which g of x, this function, is less than or equal to c, well, this is going to be of the order of c. So this is basically telling you, if you restrict your function g to some interval sufficiently close to 1/2, when your function g cuts the interval at 0, it cuts through the axes, cuts through the x-axis at 0, you're going to be cutting at an angle. You're not going to see a double root. And using that, you're able to say, get this expected behavior, namely that the measure of those points which are in this neighborhood of 0 of size c is going to be of the order c. Okay, so that's a really useful lemma, and the reason you can't go beyond 0.668 is because when you go past it, you can find functions g which are going to have a double root, so you wouldn't get this sort of estimate. So yes, so using this this transversality estimate, this lemma on the previous slide, what Benjamini and Solomiac can do is they can show that if you look at this pair correlation quantity we saw a few slides ago, and you integrate it over some interval lambda 0 to lambda 1, well, this is going to be of the order s times 2 to the n. Big O of s times 2 to the n. Okay. So how are we able, well, first of all, how are we able to do it before I explain why it's useful? So the key observation is that if you look at the two images of z corresponding to different words, well, essentially what you're seeing is one of these functions g, which we had on the previous slide, which we know a lot about how they cut through the x-axis, for which we have these strong measure bounds. So we have one of these functions multiplied by lambda to the k. And the lambda to the k causes a little technical problem, but certainly nothing insurmountable. And then you can use this lemma of Solomiac to get some strong bounds for when when you're going to have two words which are going to be close to each other, and that allows you to get this big O of s times 2 to the n term. Okay. So what can you do once you have this proposition? Well, it's a fairly simple application of Markov's inequality to show that if you pick your s to be very, very small, then for most lambda between lambda 0 and lambda 1, this set is going to be small in some sense. It's going to be, a very small constant times 2 to the n. Okay. So, and it shouldn't be surprising that if you know that the cardinality of all pairs, such that if you look at their images are close, is going to be less than or equal to some constant times 2 to the n, then the set of specific words for which there exists another word, which is going to be close to it, this is also going to be at most some very small constant times 2 to the n. Okay. And with this in mind, you can establish the existence of a large, well-separated set. So if you get a good bound for this quantity here, it's not at all difficult to show that then amongst all of these images, you're going to have a large, well-separated set. Now, all we've done is we've explained how you can have a large separated set for a typical lambda at a particular level n. To prove these measure statements, we want to be able to say for maybe for a large set of n, for infinitely many n, we want n for which along we're going to see along a collection of n for which we're going to have strong divergence. To do this, there are some extra tricks we need. Particularly, there's some kind of neat application of Fatou's lemma, which allows you to go from, well, which allows you to say something quite quantitative about the set of n for which you're going to have these large, well-separated sets. Okay, so this is just a bit of an insight into how you how you prove the existence of a large, well-separated set. Now I want to come back to this third question I mentioned at the start, which says, okay, does this approach give you any kind of new insights, tell you anything new about existing work? So, so I want to talk about a problem called the 013 problem. And this problem is concerned with this set here, this set C lambda, which looks a little bit like the middle third Cantor set. You take a lambda between 1/2 and 1, and then you look at all power series with coefficients 0, 1, and 3 evaluated at lambda. And this C lambda is the self-similar set. It's the invariant set for this IFS here. And the questions people were interested in were, what is the Hausdorff dimension of C lambda? And does C lambda have positive Lebesgue measure? And just a comment that once you're past 2/5, C lambda is an interval, so this question isn't particularly interesting. But if you're less than 2/5, it's not at all obvious what the Hausdorff dimension will be and whether it will have positive Lebesgue measure. So what is known? So quite an old result, Polycott and Shimon showed that for Lebesgue almost every lambda between 0 and third, the Hausdorff dimension is log 3 divided by minus log lambda, which is what you'd expect it to be. Then when does it have positive Lebesgue measure? Well, Solomiak in 1995 proved that for Lebesgue almost every lambda between a third and 2/5, C lambda is going to have positive Lebesgue measure. And more recently, if I combine results of Hochman and Schmerkin and Solomiak, I can strengthen these statements to say that in fact the set of exceptions is going to be of 0 Hausdorff dimension. So we have very strong results which say outside of small sets, we know what the Hausdorff dimension is going to be and what the Lebesgue measure is going to be. And what I want to explain to you now is how using these techniques, using these ideas which allow us to construct these well-separated sets, we can prove this result of Solomiak fairly cheaply, that for Lebesgue almost every lambda, C lambda is going to have positive Lebesgue measure. So how do we do this? So yeah, we can give a pretty short, snappy proof of Solomiak's result. So what do? We can show that for Lebesgue almost every lambda between a third and 2/5, there's going to be two constants such that for infinitely many n, we're going to have a large set of words, Sn, so of cardinality of the order 3 to the n, such that all of the images are going to be separated by some constant C2 divided by 3 to the n. So this is just a particular instance of this first key step I mentioned a few slides ago, where in fact I haven't even insisted that it's over a large set of natural numbers. I'm just asking for infinitely many natural numbers. We're going to have the existence of these large, well-separated sets. Okay. So once you have these things, it's really easy. What you do is you know that your limsup set has to be contained in C lambda. So my limsup set here, I'm looking at approximations of the order C2 divided by 3 to the n. This is just kind of a clump. There's a all these intersections and unions might be a bit worrying, but there's nothing too crazy going on here. I just have that Lebesgue measure of my fractal set. Well, my limsup set is contained within it, so it's going to be larger than this. Then just by continuity of the measure, I know that the Lebesgue measure of this the intersection over all n is just going to be the limit as n goes to infinity of the measure of these unions. But because I know that my lambda, so for my Lebesgue generic lambda, I'm going to have infinitely many n, such I know I'm going to have these large, well-separated sets. Well, instead of taking the union over all n for all words, I can just pick one of these n for which I know this large, well-separated set exists, look at the measure coming from this large, well-separated set, and I'm going to get this quantity here at the end. I get C1 times 3 to the n because that's how many points I know I had. And I know I get 2 times C2 divided by 3 to the n because that was how well things were separated. Okay, so this gives me positive Lebesgue measure for free. So it's very, very simple, very simple proof of Solomiak's results, which was, this problem, the 013 problem was an important problem at the time, but we can kind of, pick up a solution for the generic behavior between the third and 2/5 for free. And this is just a comment to some of the people who are a bit more well-versed in fractal geometry. We can also prove using very similar ideas that almost surely the Bernoulli convolution is absolutely continuous for Lebesgue, almost every lambda between 1/2 and 1, which was proved in the same paper where this solution to the 013 problem was given. Okay, so I'm almost at the end now. I just want to finish by posing some questions. So right at the start, I mentioned that if you have an exact overlap, then absolutely you cannot have a reasonable analog of Khintchine's theorem for your iterated function system. But the question is, okay, somehow, is this the only mechanism preventing this from happening in some general sense? We saw that for this family for which we can be very precise, we see kind of differing degrees of Khintchine behavior, but we're still seeing some sort of degree. You know, I'd be very interested in a statement which went along the lines of, for a general family of iterated function systems, in particular, maybe for the Bernoulli convolution, you either have an exact overlap or you see some weak type of Khintchine behavior. I'd be very interested if a statement like this were true. Next very natural statement is, how large is the set of badly approximable numbers? And well, the first question to ask, I suppose, is what is an appropriate notion of badly approximable here? And this is in fact quite a subtle question. So if we think about Bernoulli convolutions, you can in fact show that there exists lambda such that Lebesgue almost every point can be approximated infinitely often with error 1/2 to the n by one of these truncated power series. So Lebesgue almost surely you're getting approximations of the order 1/2 to the n, but there are going to exist certain bad points in your invariant set for which you cannot get an approximation better than a constant times lambda to the n. So in Diophantine approximation, we know somehow the scale of approximation when we're thinking about badly approximable numbers, we're interested in somehow replacing the constant with an arbitrary small constant, and we know we can do this for a Lebesgue generic number. In this framework, we're in fact seeing an exponential jump. There are numbers which you cannot do a better approximation than that, which just comes from the contraction ratio lambda to the n. Yet, for a Lebesgue generic number, you're going to have approximations of the order 1/2 to the n. So we have this quite significant jump. And then you have other values of lambda for which you can show through different methods that you can approximate by a constant times lambda to the n for any sufficiently small constant for any point x. So we're seeing again some very so it's very unclear what the right definition of badly approximable should be here. So it's quite an interesting thing. I find the existence of this jump where this exponential jump in this fractal framework quite interesting when you compare it to the more traditional Diophantine setting where it's just this whether you can replace a constant with an arbitrary small, well, one with an arbitrarily small constant. And yes, and just a more concrete question, one I'd very much like to know the answer to, is it true that for Lebesgue almost every lambda between 1/2 and 1, Lebesgue almost every x is going to be contained in this limsup set here, where I'm not even asking for any approximation, h divided by 2 to the n, I'm just saying, okay, can you do it for 1 divided by 2 to the n? I'd be very interested if this could be proved. This is, I have no idea how to prove this. It seems a very difficult problem. But yes, that was all I wanted to say. Thank you all very much for listening.
Thank you, Simon. Why don't we thank our speaker? And are there any questions or comments? Well, I have a question about this good condition that you impose on H. So did you say that it necessarily has to be there? As in, if you don't make these assumptions, there are counterexample functions?
So okay, so you have to have some sort of condition there because I had this well, we had this statement here where we saw a negative result. This fourth statement here for Lebesgue generic number, we can have so if you're badly approximable, then you can find a H which are going to have divergence yet zero measure. So you have to have something. But the specific, the specific definition of good I gave, it's an artifact of the proof. It's not there's nothing particularly deep here. Somehow the first statement here, this density, this stronger notion of divergence, this comes from this step where I go from the existence of this comment I made that it's fairly easy to show that at a particular level, typical lambda is going to have a large, well-separated set, but then showing that a typical parameter, you're going to have lots of levels. Somehow the step by which you go from one to lots, the lots you get is going to be defined in a particular way such that this definition is amenable to these sets. So maybe the sets which I can say I have a lot of, maybe they have positive upper density quite close to 1, which is why this why we see this upper density appearing here. The second statement is more to do with about stepping from positive measure to full measure. You only need the first statement. Without the second assumption, you can often prove positive Lebesgue measure, but if you want to prove full Lebesgue measure in your set, you need this type of a condition, or at least I need this
the regularity one.
Yeah.
Yeah. So the second one is rather standard, and the first one is interesting. So, what's the simplest function for which the first condition does not hold?
So I played around with this, and I think if you take 1 over n log n, it doesn't work.
Oh, really?
Yeah.
Interesting. Okay. Yeah, it's a nice exercise.
Yeah.
I have one question. So in your statements, you have for all z in some interval 1 to 1 plus t, right?
Mm-hmm.
So is there any statement where you can prove for x comma z in, let's say, R2?
So let me just bring the statement so we know what we're talking about. So yes, I fully expect. I mean, if you were to take perhaps a product system, I imagine things would carry over in a fairly straightforward way.
Okay.
Somehow the good separation properties you would get when you were to consider higher dimensional systems, well, they would translate over in a very nice way. So,
but does your does your set depend badly on z? If you change z,
no. So when you look at because all your contraction ratios are the same,
yes.
And when you look at all the level n images, they're just slight translations of each other.
Right. So it doesn't matter which z you take.
So if you know you have one z which is good, then all z's are good. But this is not the case when you have different contraction ratios. Mm-hmm. And this often means that the statements when you have different contraction ratios become unfortunately a bit more complicated. But yeah, it's a simple thing.
Thank you.
Is there something like Yarnik-Besikovich in this setting? So like in your Khintchine type statements, if you have a 0 measure situation, can you say the dimension?
So for many of these, or for many of these systems, your invariant set. Okay, well. So you can, if you were also to insist that your invariant set was to be R-force regular. So for instance, if your invariant set was an interval, it's R-force regular, and then you can use the mass transference principle to pick up these sorts of statements for free.
Oh. All right. Oh, cool.
Also, is there any Dirichlet type of theorem? So the theorems that you are stating is kind of where you have one inequality, but
so this is kind of so Okay, so there is a kind of a work in progress here, which is kind of quite interesting, where you can think about, so when you're interested in uniform approximation, so somehow it's easy to see that a point can be uniformly approximated with error, say the contraction ratio to the n. This is pretty easy, but you know that Lebesgue typical point can be approximated maybe by the number of words at level n. So these things don't definitely coincide. And what you can show is that for certain, so somehow you could ask yourself, okay, what is the correct rate for a Dirichlet statement? Is it going to be the one coming from the contraction ratio, or is it going to be the one coming from the cardinality of the words of length n? And in fact, it's both of them and everything in between. So so this is something I have to do at some point, but for a particular iterated function system, when you ask for an analog of Dirichlet's theorem, you can, a particular parameterized family, for each, you can find for any number between the contraction ratio and the number of points, you can see that the best uniform approximation you can get is going to be determined by this number. Okay, so somehow you get quite a spectrum of behaviors when you look at when you ask for a Dirichlet type theorem.
Okay, so it depends on both. I mean, something in between these two numbers.
So you can achieve the ends. You can have systems for which the best uniform approximation you can get is going to be given by the contraction ratio to the n. Then you can have the opposite extreme, and you could have statements for which every point can be uniformly approximated by the number of points at level n.
Okay.
So yes, and then everything in between.
Interesting.
Other questions? Well, if not, why don't we thank Simon again?
Thank you.
Thanks, Simon. Nice talk.